Hello. In today's video, we'll be going over LeetCode question 74. Search a 2D matrix. Let's head over to my Microsoft whiteboard. Here's the question. We are given some m by n integer matrix. A matrix is a matrix with the following two properties. Each row is sorted in non-decreasing order, which means that the row is sorted in increasing order. The first integer of each row is greater than the last integer of the previous row, which we see in the picture, where we have 1, 3, 5, 7 sorted in increasing order. The next entry of the second row, that being 10, is higher than the last entry of the previous row, which is a nice way of saying the entire matrix is sorted in left to right order, going from lower to a higher value. Given an integer target, we return true if target is in matrix or false otherwise. Our solution must be order log m by n time complexity. Here's an example. We're given a matrix containing the values 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, and 60, with the target of 3. Well, 3 is in the matrix, therefore we return the value of true. So let's go over this one more time. A 2D matrix can be considered an array of arrays, a list of lists, a vector of vectors. So, given that matrix, which is also sorted, how can we find a given target? Let's look at program design. A linear approach, which is also a brute force approach. We start at the first array and traverse all elements until we find the target. If found, we return true. Else, we will jump to the next array and repeat the same process until we find target. If this doesn't happen and we exhaust the matrix, we just return false. A linear approach could work, but it will be very inefficient. We could improve using a binary search. Remember, the matrix is sorted, so we can use the logic of binary search on each individual array. In this way, we'll basically be doing the same thing as searching each array, but instead of actually searching each array, every time we do binary search, we would cut the array in half. But we can improve even more. We can further improve. We know that each sublist is sorted. Therefore, we only need to consider the list where we expect our target to be. And what do I mean by this? Let's say we've given some list. So 1, 2, 3, 4, 5, 6, 7, and 8. And let's say the target value we are looking for is the value 7. Here's the thing. There's no point for us to search the first array. Why is that? Because even though the first array at position 0 is 1, which is less than target, but is 7 less than the array at the last position? No, because 7 is not less than 4. Let's look at the next array. Now we are considering this array. Is the array at the 0th position, so less than target? Yes, because 5 is less than 7. Well, what about the array at the last position? Let's say position -1. Well, is 7 less than 8? Yes. Therefore, 7 must be or can be in that array. And this is the logic that we would be using in our solution. Let's head over to LeetCode. Alright, here's our first part of the solution. We create some function called bin search, which is just binary search. We pass it in our vector, could be a list, could be an array, does not matter. So we pass it in our vector and the integer called target. And this is just simple binary search, so I'm not going to really go over it. Its purpose is to determine if a value is in a vector, an array, or a list. Here is the actual solution. So we have our class solution with a public function called search matrix, which takes as input a vector of vectors, thereby creating a matrix, and an integer target. And then all we have to do is loop over or loop through each individual vector within our matrix. And we determine if v.front is less than or equal to target and v.back is greater or equal to target, then we will do binary search in that vector. And if binary search, which returns a boolean as we see here, ends up being true, we return true. If not, we'll just return false. Now, this solution will work. And it will give you a runtime complexity of 0 milliseconds. And that's the solution. This solution will also work for search a 2D matrix 2. And that's it. Although here it's not as fast, because as we see here, we determine that our matrix gets much larger, but still pretty good, with the least runtime being 107 milliseconds. And that's the video.